Okay, this is exam 2 for Physics 202. First of all, multiple choice, which is worth 20 points total. Here we have charges that are enclosed by Gaussian surfaces. We just want to rank their fluxes. Well, if you remember from our equation sheet and our definition of our Gauss's law, the permittivity of free space times the flux is equal to the Q enclosed. So Q enclosed equals that permittivity of free space times our flux. So it doesn't really matter the size of the shape. Your flux is always going to be related to your enclosed charge. So because of that, we know that these three all have the same flux. A, C, and D. So by that, we can say that this has to be the right answer. And then further, this one and this one have twice the charge, so they have more flux and they're equal. So B is the right answer there. The amount of electric field passing through a surface is called the electric flux, where it's E dot dA, the integral of E dot dA, where it takes the dot product means that you have the electric field vector that is in the same direction as the area vector when you dot those two. So if you have an electric field that is off in some other direction, then only a component of it that's in the same direction as dA is going to contribute to the flux. The vectors in this diagram represent the electric field. Arrows are all the same length. What type of charge does the box contain? So here we're looking for what is the net flux in. Look, we have three fluxes that are positive and then one flux that's negative. So I'm going to have a net positive flux. That means I'm going to have a net positive charge. So there could be positive and negative charges in the box, but I'm going to have an overall net positive charge, more positive charges than negative charges. Gauss's law applies to closed surfaces. What is the equivalent capacitance of this circuit? Okay, well, these two add up to give me 2, and then these three, 2 plus 1 plus 3, add up to give me 6, and then I have a 3 and a 6 in series, so that's going to be 2 microfarads. What is the voltage of the 6 microfarad capacitor? Remember, I have 8 volts here, I'm going to have 8 volts, or excuse me, 12 volts here. I'm going to have the bigger voltage across the smaller capacitor, the smaller voltage across the bigger capacitor, so the answer here is C for number 6. This diagram shows collection of charges. At what point is the potential equal to 0? Well, remember, let's just take point B, for example. The potential is 0 if the negative and positive charges are equidistant from that point, as it is here and here, here, and here. And if we pick another point on this, say point C, these two charges are equidistant, these two charges are equidistant, they're also opposite, so the potentials cancel out, and likewise there and there. As a result, all of these, you'll find if you go through them all, have a potential equal to 0. Parallel plate capacitor initially has a potential difference of 10 volts, and then it's disconnected from the charging battery. If it's disconnected from the charging battery, that means that Q is constant. And I know that Q is equal to CV. This remains constant. If I double the area of the plates, remember C is equal to epsilon naught A over D. So if I double this, I double this. If I double the area of the plates, that means I halve the voltage. So where it was 10, now it's 5 volts. So B for number 8. Where is the electric potential the least? Well, remember V is KQ over R. So when R is big, V is small. So D has the smallest, and then A is also along that equal potential line, so it also has the smallest. So B for number 9. And electric potential is a measure of energy per charge. This would be electric field. This would just be described by Coulomb's law, and we haven't described momentum per charge. All right, you have potential described by this function. What is the electric field in vector notation? So remember, in general, my electric field is negative del V del S. So EX then is going to be the negative of that function, the derivative of that function with respect to X. That's going to be 3y, just 3y. Y is equal to 1, so it's going to be negative 3 times 1, or negative 3. EY is going to be negative 3x minus 4z squared. Putting in the proper coordinates for that, I get negative 6 minus 16 equals positive 10. And then EZ is, this is 0, so it's going to be minus 8yz. Actually, it's going to be the negative of minus 8yz, which is going to be positive 8yz, which is going to be negative 16. So my answer then, the electric field in vector notation, is going to be negative 3I plus 10J minus 16K. That's in newtons per coulomb, or you could give it in volts per meter, as we see here, volts meters. That is an appropriate unit for electric field. Beginning with Gauss's law, describe the equation for the electric field due to a point charge. We'll begin with this, Q enclosed over epsilon naught. Remembering that our flux here is just the electric field times the area. We know it's a little more complicated than that. It's actually the dot product of those two vectors, but we'll assume that they're in the same direction and that we've integrated over that area. That's equal to Q over epsilon naught. And then if I assume a spherical surface, my area is 4 pi r squared equals Q over epsilon naught, and then E is Q now we recognize that K is equal to 1 over 4 pi epsilon naught, and then that gives us the expression for the electric field, KQ over R squared. And then we could further say, since E is a force per unit charge, then we can further, I didn't expect you to do this, but you could further derive Coulomb's law. I mean, the electric field comes from Coulomb's law. So in Gauss's law, we have the Coulomb's law. It's because it's a spherically symmetric force. So consider this configuration of charges. What is the potential at point A due to the three charges? What is the potential at the entry of three charges? And then how much work would it be to take a charge and put it right here? First thing we want to do, let's just recognize that this distance here is 5 meters. Excuse me, not that distance. We'll need that distance later. But let's recognize that this distance is 5 meters. This is 4 meters. This is 3 meters. And now for part A, we want to calculate the potential at this point due to these three charges. So for part A, I'll have V is equal to K Q1 over 3 plus K Q2 over 5 plus K Q3 over 4 meters. 9 times 10 to the 9th times 3, excuse me, being careful here that this is a negative value. That charge carries a negative potential divided by 4. And then we get some things that cancel out. These all cancel out. And then I get this cancels here and leaves me 3. This cancels here and leaves me 10. This cancels here and leaves me negative 4. So I get, what's this, 9 plus 90 minus excuse me, not 9. This should be 27. 27 plus 90 minus 36, and that's equal to 81 volts. So that's the answer for part A. For part B, you were supposed to find the potential energy for each of these pairs. So I find the potential energy for these two pairs, potential energy for these two pairs, and then the potential energy for these two pairs. I'll just do one of those. let's just do the potential energy for Q1 and Q2. It's going to be 9 times 10 to the ninth. So our Coulomb's constant times Q1, which is 9 times 10 to the minus 9, times Q2, which is 50 times 10 to the minus 9, divided by R, which is 4 meters. And then I find this value, and I add it up also, K Q2, Q3 over R. That R was 3 meters plus K Q1, Q3 over 5 meters, recognizing that this Q3 is a negative value, so that last term is going to be negative. If I add all those up, I find that that is 1 times 10 to the minus 6 minus 2.4 times 10 to the minus 6. Yeah, so I also have a negative here, minus 2.6 times 10 to the minus 7. And then that gives me the total energy, which is minus 1.6 times 10 to the minus 6 joules. For part C, it was supposed to be really simple. The work required to take a 2 nanocoulomb charge and place it to point A is going to be equal to Q times delta V. However much energy is required to move that 2 nanocoulomb charge from an infinite distance away, changing its potential by 81 volts. So I just say 2 times 10 to the minus 9, that's my nanocoulombs, times 81 volts. And then that gives me 1.62 times 10 to the minus 7 joules. So that's the right answer there. Some of you did do it in a lot more complicated way, where you can figured out the total energy to combine those 4 charges. And that was fairly complicated, but it was right nonetheless. Okay, let's look at this circuit. Unfortunately, as I said in class, I meant the circuit to be a little bit easier, just for the numbers to work out easier. But you still did really well, and I graded it fairly leniently. I was looking largely that you had the relationships correct for the various capacitors, and I'll show you what I mean by that. But first, let's just redraw this. I have my 12 volt. I have over here 3 branches. In the middle, I'm going to have 2 capacitors. This is going to be a 3, and a 6, and a 6 over here. These all come back together, and then I break into 2 more. This is a 4, and a 2. All right, and then I can combine some of these. I get a 3 and a 6. That's 2 microfarads. A 4 and a 4, 1 over a quarter plus a quarter. That's also 2. And then I get 3, 2, and 6. And this is where I messed up, actually. These should have been more even, but this one, a 3 plus 2 plus 6 is 11 microfarads. And 2 plus 2 is 4 microfarads. And then to find my equivalent, I say 1 over 11 plus 1 over 4. And that answer was, I think, 2.9 microfarads. So that's my equivalent, 2.9 microfarads. And then you had to find the equivalent charge, which is going to be 2.9 microfarads times 12 volts. That's at about 48 or so. Or 36 rather, 34.8. So we'll just call this 35 micro. We'll keep one decimal place, 34.8 microcoulombs. So that means that I have 34.8 microcoulombs here and 34.8 microcoulombs here. Now I can find the voltage. Remember, my voltage is Q divided by C, so my voltage up here is going to be 34.8 divided by 11, which is 3.2. And down here it's going to be 34.8 divided by 4, which is 8.7. All right, so now recognizing that, if I have 8.7 here, I must have 8.7 volts here. And here, I have to have 8.7 divided by 2, because these two capacitors are identical, they will both have 8.7 divided by 2, which is we'll just call it 4.4 volts rounding off. So both of these have 4.4 volts. Now we can start giving some answers here. C5 and C6 are both 4.4 volts. I was looking particularly that these be equal, so even if you got all the numbers wrong, I gave you a lot of credit if you just got the relationships correct. So if you had these two equal, I only counted off like 5 or 6 points. And then this C7 right here is the same as here. It's going to have 8.7 volts, or really, yeah, 8.7 volts. And I was looking that this was twice this value. Okay, now on the top branch, I have 3.2 volts. So I'm going to have 3.2 volts here and 3.2 volts here. So that is 3.2 volts, 3.2 volts. And then here, I have a 3 and a 6. Between them, they have 3.2 volts. So the charge on this 3 and the 6, which is going to be our Q equivalent, it's going to be 2 microfarads. That's my capacitance, and that is the equivalent of these two capacitors times the voltage, and the voltage across those two capacitors is 3.2 3.2 volts. And so that charge is going to be 6.4 microcoulombs. And so I can go ahead and put that up here. 6.4 microcoulombs. And then I can find my voltage, and where my voltage is Q over C. So for C2, which is 3 microfarads, it's going to be 6.4 divided by 3, which is 2.1 volts. And then for V3, it's going to be 6.4 divided by 6, which is 1.1 volts. So I was looking that these two be equal, and I was looking that you had the right proportion on these two. And if you did have those things, as I said, I didn't count off that much. This was 2.9 microfarads, and now it's just a matter of going through and multiplying V1 times C1 to get, what's that, 9.6 microcoulombs, 3.2 times C4, which is 6. That's 19.2 microcoulombs. This is 4.4 times 4, 17.6, 17.6, and then 8.7 times 2, 17.4. Is this the last one? Yes, okay, so let's go ahead and do this one. First I want to know the electric flux through the Gaussian surface. Notice that my electric field only has I and J components, so the front and the back, the flux through the front face, that's this face coming out, and the flux through the back, because those are both in the K direction, their dot product with E is going to be equal to 0. So all I'm really concerned about is the top, bottom, left, and right. So let's do each of those, top, bottom, left, and right. So for the top, I need to find out what is my dA. For the top, my dA is plus 15J. And my electric field, or phi, is going to be E dot dA, which is going to be 3xi minus 4j, dotted with 15j. And of course the I dot j term goes away, and we're left with negative 60 j dot j, which is just equal to 0. So that's the top. And then the bottom, in a very similar way, the only difference is that now this vector is going to be negative, so our flux is going to be positive 60 because it's exactly the same, except now I have a negative 15j. So that's the top and the bottom. The left is going to be 3xi minus 4j, dotted with the left vector, which is minus 9i. So these will be the only terms, but on the left side, because x equals 0, the flux is also going to equal to 0. This x will plug in here and give me 0 flux. So far I have 3 zeros and a negative 60 and a positive 60, and then the only thing left is the right side, and on the right side, my dA, my area vector, is going to be, plus 9i. E dot dA then will be 3xi times 9, or 3x times 9, I dot I. I left off the j term there because I dot j is equal to 0. So that's 3x times 9. Here x is 5, so I have 15 times 9, which is equal to 135. All right, so now I add up these three values, and I get my total flux as 135. Now, Newton meter squared per Coulomb. Now, part B, pretty simple. Once I have the flux, Q enclosed is just epsilon naught times phi, 8.85 times 10 to the minus 12 times 135. And you get the charge that's enclosed inside that Gaussian surface as 1.19 times 10 to the minus 9 coulombs, or 1.2 nanocoulombs. There's multiple choice answers. That's the end.